So now let's discuss about the second symmetry element, which is plane of symmetry. And this is also called as reflection of symmetry. Here we see a reflected plane, reflected parts of the particular element. It is represented by sigma, and these are of three types. A sigma v, which represents vertical plane, a horizontal plane, which is represented by sigma d, and a dihedral plane, which is represented by sigma d. So what is vertical plane and horizontal plane and dihedral plane? To know about that, we know that so in sigma v, principal axis, which is the highest ordered axis, is parallel to a plane which is passing in a molecule, and in sigma d and sigma h, when a principal axis is perpendicular to plane that is passing through that molecule, and in sigma d, principal axis is parallel to plane but bisect with two C2s. What it means is, if we put a plane, then two C2s must be followed. To know more about the vertical plane, let's take an example of H2O. As we can see, there is one principal axis, C2 axis, and there is one plane. And if we consider this is an axis, just like here, X, Z, and this is Y, then the plane that is passing here is an XZ plane, just like that. So here, so if you put a sigma v1 here, then it will convert this will reflect these hydrogens in opposite direction, so this will give equivalent structure. So vertical plane is possible, and we can do another plane just like in this direction, which bisect all the three atoms present, and this is also a plane which is parallel to the C2 axis or principal axis. So in H2 molecule there are two planes possible, and it is sigma v, two sigma v's. So let's take another example to understand plane of symmetry. If we talk about BF3 molecule, as we can see here, one C3 axis is present, principal axis, which is principal axis, and if we put a plane parallel to C3 axis, which will cut this molecule, and one plane from here which will cut this molecule and reflect these, and if we cut one from here, so in this molecule there is three sigma vertical planes present, which will cut from B and F one time, B and F one time, and B and F one time, and reflect these two molecules. So, and one horizontal plane. What is a horizontal plane? Horizontal plane is just like that. A C3 axis is passing, and here this is an horizontal plane which is passing from this all the F's, cutting all the molecule, all the elements present in there here, and it is perpendicular to 90 degree. So we can make an assumption that if the equal sides are present in a molecule, just like here F is equal sides, so the Cn axis, which is our principal axis, or in case C3, it is perpendicular to 3 C2s, two C2s are present here. Now let's talk about sigma d. What is sigma d? It is a dihedral plane. So to see a sigma d in molecule, let's take an example of PtCl4. So in this molecule, as we can see, there is one C4 is present which bisect this molecule in equal to So this is a square type of molecule. So as we can see, one C2 axis is coming from here, cutting all these elements, and one is from here, and one from the middle. Let's make it another color. One from the middle and one from here middle. So there are four C2s present, and if we take what is the dihedral angle, and if we cut a C2, just like when a principal axis, when a plane is passed from C2, from C4 to C2, all the way from the molecule, cutting that in equal halves. Let's take another example of benzene and see sigma d here. Let's go to this side. It's a symmetry order side. As we can see, this is a structure of benzene, and we can see all the axes here, just like the principal axis, the C6 axis, which is passing through the middle. Here, and we will be seeing the next axis here is a C2 axis, three C3 axes. So these are all the C2s which is passing through the atom, and this is the axis which is passing through the middle of the atom, say, or between atoms. So these are in between atoms, and if we put a sigma d here, just like that, this is passing from, this is the sigma d that we are talking about. In benzene ring, when the in between atoms, if we cut a molecule by placing a plane here, then it is bisecting these axes. Well, to understand more about this, let's take another example. Let's take an example of ammonia. As we can see, a 1C3 axis is passing, which is the principal axis. So here, how many sigma v's are present? So there are 3 sigma v's are present. If we talk about sigma d, there is no sigma d is present here because of no availability or crossing of the any C2s. And if we put a sigma h, there is no horizontal plane present also, so it is not possible. So there are only 3 sigma v's are present. So if we talk about axis of symmetry here, it is C3 perpendicular to 3 C2s, and plane of symmetry, it is equal to 3. Let's discuss this molecule in the orthropine side. So this is an ammonia molecule. As we can see, in blue color show the nitrogen, and these 4 hydrogens are arranged. So let's see one C3 axis which is present here. So this is the C3 axis coming from all the way from the middle. And if we talk about the vertical planes that we talk about, so these are all the 3 vertical planes which is cutting these molecules. Well, to know about the graphs or the plane that we are passing, just like what type of plane, let's take an axis, a z here, and an x here, and a y which is above the plane. So as we can see, the coordinates of this is x, y, z. If we put a C2 here, or if we do 180-degree rotation along the x-axis, if we put x-axis in a place and place a C2 here, so these 2 molecules will change. So here the structure will be, the x will remain in the same position, and this y will go back, and this z will go down, so it is minus y, and this is minus z. So this is x minus y minus z coordinates. And if we again do the same along let's see along y-axis, C2 along y-axis, so that y will remain in the same position, and this x will go from here to here, and this z will go from here to up. So z will go up and this x will go minus x. So the final coordinates of this is minus x minus y and z. So to that, let's discuss a question which is asked in CSIR net according to this concept which I told you just before. So the question is a sigma x2 and a sigma yz, a sigma xz and a sigma yz, so that the resultant coordinate will be equal to. So in this diagram we put all this process, what will be the final coordinate of this molecule. So if you put a sigma xz first, this is given first, so this will be first, this is second, this will be second. So if we put an xz plane along this plane, so this y will be go from behind. So if you put this plane here, then y will become minus y. This is the final coordinate here. And after that we put a sigma yz and it's along the yz plane, so y and z. So this will be y and this will be z, this plane. So according to this plane, this z will go from here to this, it will reflect like that. So this is the final coordinate x, y, z. So the question is resultant coordinate will be equal to what? So if we put the cz along the z, c2 along the z axis, if we put z axis, c2 along the z axis, if we put c2 along the z axis, then this will become minus x and this will become minus y. So this will be the final resultant, which will be, this coordinate will be same as this. So the final answer is this. Now let's discuss about the next symmetry element, which is center of symmetry. It is an easy as compared to both back discussed. So it is represented by I, and it is also called inversion center. So to identify whether a molecule has a center of symmetry or not, in short COS, let's take an example of N2F. It is a trans molecule. So as we can see, if we go from the middle to here and middle to here, so center of symmetry I is present. It's called inversion of center. So these are some few examples. Let's discuss whether the center of symmetry is present or not in this molecule. So how will we check? So if we put this alkene in a center, if we go from here and here, the same elements are present. If we go from here, same elements are present. So center of symmetry or identity is present here. Let's talk about this BF4 molecule, BF3 molecule. So here if we go from here and come back here, so there is no fluorine, so center of symmetry is absent here. No center of symmetry present in BF3 molecule. And let's check here in this molecule one, if we go from here, a chlorine is present. If we go from here, chlorine is present, and again here hydrogen and hydrogen. So here center of symmetry is present or inversion is present. In benzene molecule, carbon is, if we put a center of symmetry here, and if we go here and here, or here and here, carbon and hydrogen is present. Either here also carbon and hydrogen is present in benzene molecule. So here it is same. So center of symmetry or inversion is possible here. Let's talk about the here, and if we put one carbon here, so here is carbon and here is nothing, again here is carbon and this will be nothing here, so center of symmetry or inversion is absent here. So these are some example of center of symmetry or how to find it. Now let's discuss about the next point group, symmetry element, which is improper axis of rotation, which is represented by Sn. It is a very important point group as compared to previous ones. It is also a little difficult to perform because here we operate two functions, just like first we rotate a molecule, a rotation is followed by a reflection. This is an operation according to which an Sn equal to Cn, and it is perpendicular to sigma. To check an Sn, if a molecule has an Sn or not, we need to first check whether it have a Cn axis, and if we put a particular plane here, and are we getting an identical structure or not. So in this example, if we pass a C2 here, then this rotation is occur and this Cl position will change, and if we put a plane perpendicular to the C2 axis, then the identical structure has been seen. So the structure that made after that is identical to this, and we know that it is similar to identity, it is similar to inversion. So if we check if inversion is present in molecule, then S2 is also present. So make a note. Now this is the observation that we get from this example. So let's take another example of S2, S4. Here we know that so this is the rotation that is followed in S4 geometry. Let's see one more time. This is the structure of allene, and this is S4. One rotate, 90-degree rotation. After that, it go back, and we will see the similar structure. So allene will show S4. So this is all for the lecture today.